We're going to start a new chapter. Very exciting. And we're skipping. We're going all the way over to chapter 12 after binary search trees. Chapter 12. And we're going to be talking about these things called heaps. Why, you wonder, are we skipping so many chapters? Well, heaps have something to do with binary search trees. And we just finished binary search trees, so it just seems like a nice thing to do at this point. So the question is, what is a heap? I knew you were all wondering that. What is a heap? Well, first of all, a heap is a binary tree, so you should all like that. That satisfies the heap property. And you go, okay, what is the heap property? Actually, it's two properties. So I'm going to say A heaps are complete. And then B, okay, they satisfy the heap property, okay, which is that every parent is greater than each of its child. So this means a couple of things. What does it mean that it's complete? Well, complete means that as a heap grows, it's going to keep adding nodes on whatever the current level is that I'm adding nodes to before I go to the next level. In other words, if this is what my heap looks like right now and it's time to add a node, I'm not going to add it down here. I'm going to add it over here. And then from here, if I'm going to add another node, it would look like this. And then from here, it would look like this. And then the next node would be here, and then the next node would be here. In other words, the point is that I don't add a node at a lower level until the level before it is complete. Okay, and note what that means. I've got one node here, two nodes here, four nodes here. There would be 8. And look at this, it's growing by powers of 2. So what's going to happen over here is I would come over here and I would fill in 8 nodes and it would move from left to right. And that would occur from left to right before I went down to the next row where there would be 16 of them. Now the other thing has to do with every parent is greater than each of its children. So for these examples, we're going to be sticking numbers into the nodes. So you might imagine something like this. If I came over here, okay, that's a heap. And in fact, if I came over here, that's a heap. Okay, it's still a heap because you'll notice that at any point, if I pick any node here, the node is greater than either one of its children. Okay, if I had something that looked like this, okay, this is not a heap, and the reason why it's not a heap is here is a node over here that is actually greater than its parent. So this is not a heap. This is a heap. An example of what's not a heap, if I had something that looked like this, This is not a heap. Even though every parent is greater than both of its children, the problem is these two nodes over here should be over here. In other words, I had a row that I needed to complete before I went down. So this is not a heap as well. Okay? Pretty simple. Now, we are going to be representing heaps as arrays, which sounds kind of weird. And it turns out you can represent any binary tree as an array if you wanted to. So let's come over here and let's look at this heap right over here. And basically, I'm going to create an array, and this will be 0, and this would be 1, 2, 3, 4, 5, and 6. So the array representation of that particular heap over there would look like the following. Okay, I'd have 100 over here, and then I would have 50, and I would have 75, and then I would have 10, 40, 65, and 3. And this raises two questions. Okay, let's call this array, let's give it a name. AR is always a good name. And I ask a couple of questions here, and I go, who are the children of AR of K? And then I ask, who is the parent of AR of K? Well, let's come over here and see if we can spot a couple of patterns. AR of 0 has children AR of 1 and AR of 2. AR of 1 has children AR of 3 and AR of 4. It looks like AR of 2 has children 5 and 6. So it looks like the way that I get the children is I take the index and multiply it by 2, and then I add either 1 or 2. If I come over here, 2 times 2 is 4, plus 1 is 5. 2 times 2 is 4, plus 2 is 6. So the children here would be AR of 2 times K plus 1, and AR of 2 times K plus 2. Okay, that was really easy. How about how do I find the parent? Okay, well, it looks like maybe what I need to do here is from either one of these I subtract 1 and then divide by 2. In other words, the parent of AR of K would be AR of K minus 1 divided by 2. Now let's keep something in mind here. Remember, this is an integer division. So for example, if I came over here and I wanted to know who was the parent of AR of 6, well, I would go AR of 6, I would go 6 minus 1 is 5, and 5 divided by 2, that gets me to AR of 2. And if I come over here, it does look like AR of 6's parent is AR of 2. If I wanted to know who's AR of 4's parent, well, that would be AR of 4 minus 1 divided by 2. Well, that gets me to AR of 3 divided by 2. And remember, that's an integer division, so that would be AR of 1. So that seems to work. So these are a couple of rules here that you should keep in mind. That one right there. And that one right there. Okay? Good. So now let's talk about how heaps are going to grow and how they are going to shrink. So let's imagine that I have a heap here. And, oh, I don't know, let's come over here and put one more in there. Okay, and what I want to do now is I want to insert a new element. And I suppose I want to insert 95. Okay, so I'm going to, first of all, if I'm inserting a new element, we know that when I'm done, the heap better have something coming down here. Okay, because we know that the heap has to grow this way. So basically what I'm going to do is I'm going to insert the 95 at the bottom. Okay, and I come over here, and here's 7, and here's 90. And now I'm going to do, I believe your author calls it trickle up. And the idea of trickle up is what I'm first going to do. Whoops, I wanted to insert a 95. So why don't we make the number correct? So the first trick that I'm going to do is I'm going to compare 95 with its parent. And if it turns out that 95 is greater than its parent, I'm going to go ahead and swap them. So I'm over here at 100, and now I have 90, and I have 60. And now I'm going to come over here, and this is going to be 95, 40, and I have swapped them, so I've got 7 over here, and 30. And over 60 here, I've got a 3 and a 7. And now what I got to do here is compare those and swap if necessary. So that's going to take me over to here now, and I get a 100, and then I get a 95, and over here I get a 60, 3, 7, under 95 now I'm going to get 90 and 40, and underneath this 90 I'm going to get a 7 and a 30. And now what I would do is I would compare the 95 to the 100, and there is nothing to do. And notice what I have now is this is now a heap. And notice that I have grown by 1, so there's an element over here. So the whole idea of inserting is we add the element at the end of the heap, okay, wherever that may be, and then we perform this operation called trickle up, which is we keep switching it with its parent until we find the correct place where it goes. And yes, it's quite possible that we may have to switch the one up here. Suppose the number that we were to add over here now, suppose we wanted to insert, and I'll leave it as an exercise, suppose I wanted to insert 107. Well, I think you can see the 107 would get inserted over here, and I would bring the 40 down to here, and then the 90 would come down to here, and the 100 would come down to here, and 107 would end up at the top. So that is the trickle up. So that is what is used for inserting into the heap. Finally, the other thing that we do is we remove things from the heap. But they're removed in kind of a funny way. Okay, we talk about popping the heap. Just like we talk about pushing and popping a stack or a queue, we actually push and pop on a heap too. And what we did here is when we inserted a 95, that was really a push. Okay, so the question is how do we pop? I'm going to say pop or remove. And the way that we do that is we start off with our original heap. Let's go to the new one that we've created here now. So here's 95, and here's 60, and here's 90 and 40, 3 and 7, and over here we had 7 and 30. Okay, so first of all, when we pop, we're going to remove this value here. Okay, so what happens is we've removed the biggest value from the heap. Okay, and then what we do is we come down here and we take the last value in the heap and we kick it upstairs. So when we kick it upstairs, we're left with this. Okay, now remember we've kicked it upstairs, so this thing is no longer here anymore. And now, just like over here, when we did trickle up, over here we're going to do something called trickle down. And the way that we trickle down is we look at 30's children and we swap it with the bigger one. So we come over here and I've got 95, and then I've got 30, 60, 3, 7, and over here I've got 90 and 40 and 7. And now what I have to do over here is I again have to compare 30 to its children, and I see that there is one bigger than it, and I pick the bigger of these two and I swap it again. So I get down to 95, and then there's a 90 over here, 60, 3, 7. I come down over here, here's 30, here's 40, okay, and here's 7. Okay, and again, I compare this to its child, but I see that it's bigger than it, and I'm all done. And we can see, again, we started with a heap here, we got down here, it has one less element. Notice that it disappeared right from the end, and we still have everything satisfying the heap condition. So what we need to do in the next video, we'll stop right here, is we need to look at how do we implement trickle up and how do we implement trickle down.